Hi, today I will be talking about our work on performative prediction in a stateful world. This is joint work with Gavin Brown and Shlomi at Boston University. Machine learning models are commonly used to make predictions about people, and this helps institutions and people in making decisions. However, such predictions can influence the behavior of the target population that they are trying to predict. And in turn, this affects the outcome which is being predicted. For example, loan applicants strategically manipulate credit card usage to increase their credit score and have better access to credit, whereas students tailor their college applications to admission criteria. In their recent work, Perdomo, Zernit, Mender, Duner, and Hard term such predictions performative. Our work builds on that of Perdomo et al. Our key observation is that the response of the target population depends not only on the deployed classifier, but also on the current state of the population. We think of state as a distribution on the features of the population. In this example, a commuter chooses every day between train or car based on the projected traffic. This example is in fact stateless because the decision of the commuter on a given day does not depend on their decisions in previous days. This is the setting of Perdomo et al. This other example, college admission criteria are changing over the years, but the information propagates at different rates across high schools based on access to counseling. This example is stateful because even if the college admission criteria stay the same over the years, the distribution of the population will change as students catch up to the latest information. Our model tries to encapsulate both of these examples. How do institutions deal with performativity in practice? One common and simple heuristic is to update the classifier so that it minimizes loss on the latest data or on the current distribution. Perdomo et al. Call this strategy repeated risk minimization. Our contributions are the following. We propose a theoretical framework to model stateful performativity, and then propose a notion of optimal strategies for the institution in this framework. We show conditions for which repeated risk minimization converges near such optimal points. Both our framework and results generalize the work of Perdomo et al. Our framework is cast as a two-player game between the institution, which deploys classifiers, and the world, which responds with distributions. At round T, the institution deploys classifier theta T, and the world responds to it with a new distribution dt. This distribution is calculated according to a transition map, which takes as an argument the previous state, dt minus 1, and new classifier, theta t. The transition map is fixed throughout the game, and in particular, it is unknown to the institution. When the institution observes this new distribution dt, it will suffer a loss on dt according to a fixed loss function. The loss it suffers comes from the current distribution, and not from the distribution that the institution was optimizing on. One possible strategy for the institution is repeated risk minimization. It chooses a new classifier, theta t plus 1, so that it minimizes loss on the distribution dt that it just observed. This model is stateful because the transition map preserves information about the distribution of the world. One key question is, how do we measure the success of the institution in this adaptive environment? Measures that are proposed in online learning, such as regret, excess loss, and policy regret, aren't quite suitable for our framework. We focus on this question. If the institution deployed just one classifier throughout the game, then which one should it choose? We define optimal classifiers in the following way. Let's have some assumptions on the transition map. With this assumption, if the institution deploys the same classifier over and over again, then the loss it experiences will converge. The optimal classifier theta is the one that converges to the smallest loss possible. With this, our main result is that RRM gives a way to converge near optimal points. With some assumptions on the loss function and on the transition map, if the institution uses repeated risk minimization, then it will converge near an optimal classifier. We assume that the transition map is jointly Lipschitz in its two arguments. Thank you.